Well, thank you very much, Michael and Mustafa, for giving this opportunity to be here and present the MathWorks workflow for integrating MATLAB algorithms directly into the Holoscan. Uh, a little bit about myself. I'm Akhilesh. I'm the industry manager for medical devices at MathWorks. I've been with MathWorks almost 8 years, supporting so many different workflows, all related to medical industry. Before MathWorks, my background was signal processing. I was doing radar signal processing for a couple of years, sounding the glaciers of Greenland and Antarctica. So kind of it was a good transition from radars for imaging to start doing ultrasound, then transition to, X-ray, CT, so on and so forth. And here we are. Anyways, so that being said, let me just get dive in. So some of us may not know who we are, so I just thought maybe I'll just include a quick video to give an introduction. Let's quickly watch this 2-minute video before.
With today's powerful computers and advanced computational methods, engineers and scientists are taking on the great challenges of our time. Renewable energy, new medicines and healthcare technology, clean air and water, smart transportation systems, and weather and climate forecasting. For decades, MATLAB has been the computational engine for discovery and innovation. MATLAB is a high-level language for easy expression of engineering and scientific ideas. A language taught at universities around the world to train the next generation of engineers. MATLAB has a vast algorithm library based on a strong foundation of mathematics that embodies the latest techniques in linear algebra, signal and image processing, communications, control systems, and many other domains. Today, millions of engineers and scientists use MATLAB as a common language for sharing ideas and collaborating across disciplines. They use it to model energy consumption, to build smart power grids, analyze weather data, to visualize the track and intensity of a hurricane, develop algorithms to optimize hybrid vehicles, and run millions of simulations to pinpoint optimal dosing for antibiotics. With MATLAB, engineers and scientists accomplish in minutes or hours what would take days, weeks, or months with conventional programming languages. They speed up their work running MATLAB on multi-core processors, GPUs, and clusters. They automatically generate C code from MATLAB algorithms, and they deploy MATLAB components into production environments. MATLAB is the language of technical computing. What can you do with MATLAB?
All right. So that was a kind of a quick high-level overview of who we are. So MathWorks, yes, you guessed it right. We are MathWorks. We are MATLAB and Simulink. And it's been a tool used for engineering and research across various industries, a lot of users worldwide. And then one of the focus industries for us is definitely this healthcare industry, right? So we have a lot of original equipment manufacturers, research institutes, hospitals, and using MATLAB every day for doing like building medical devices or doing like research in the medical domain. So for medical device development specifically, there are three things where MATLAB is used extensively. First part, which most of us may already be aware, is accelerating like the research and development, where you can build quick prototypes using the MATLAB language and test out the concepts. But then the two other workflows, which are not so well known, but it is very powerful, are transferring those prototypes to products. And this is one of the things which we'll look very closely today. So we do have the capability to automatically convert MATLAB into code, which can go on embedded microcontrollers, NVIDIA GPUs, ASICs and FPGAs, and also the enterprise system. And lastly, because medical device is also is a highly regulated industry, complying with regulation and standards is a key. So if we take those prototypes transfer into the actual products and we do not meet the regulatory requirements, then we are only getting the job half done. So there's a big workflow associated or solutions available inside MATLAB to comply with the various regulatory bodies while we are building those algorithms. So here is one example of one such company like Khwaja Medical Technology. They wanted to build ECG analysis software to detect cardiac abnormalities, and they used the entire three workflows where they quickly prototyped algorithms, generated code, and not just MATLAB code, but the MATLAB code was also converted to C code and then also the GPU code to deploy on a Jetson environment. And then they used also the certification workflows to submit their 510Ks and achieve the 62304 certification. And they were able to put their device out to market in a matter of just months. So that being said, in current era, right, like medical devices, so that was kind of the high level overview of MathWorks tools being used, but we are seeing like significant advancement in the medical technology year over year. And a good example is ultrasound imaging. And probably today also, and since morning, we have seen some of this. But over the years, what we've seen is the systems have become more complex. Back in the day, it was static imaging. And now in the late 2000, we started to get some video streams. And recently, we are also seeing real-time live streaming with capabilities such as like portable ultrasound or the 5D ultrasound, where you can see the videos, and then you can also see various features like the skin color of the baby in case of an OBGYN ultrasound. And then AI is also extensively being utilized for either aiding with clinical diagnosis or improving the image quality of the ultrasound. So enabling technology behind making this happen is one of the key enablers is the faster processing speed of frame rate, and these faster computing speeds are translating directly into the enhanced product features. But having said that, for an OEM perspective, there still are a lot of challenges when it comes to we want to get these advanced feature out in the market in a much shorter time. And when we want to get in the shorter time to stay competitive, there are always a lot of bunch of challenges that comes across our way. So regulatory compliance is definitely one of them, which I talked about earlier. But then the whole thing from design prototyping to coding to testing, validation, deployment, everything kind of takes a lot of time. And the longer time we take in the development or putting the stuff out in the market, we kind of lose our foothold and it leads to like lesser profits. So long story short, we do want to get those faster compute speed, enhanced features in the medical device in a very short amount of time. And the way to do that is when we combine tools like MathWorks and NVIDIA together to be able to have this integrated hardware and software platform for the entire medical device software lifecycle. So what that means is imagine the scenario where you have uh, direct capability of connecting your software to the accelerated hardware, such as NVIDIA GPUs, and you can do all of this design prototyping, automatic code generation, testing, and then also provide the VNV documentation for regulatory submission purposes. Uh, and that definitely would make your device come out to the market in a much shorter time. So VNV, a little bit more emphasis on VNV aspect is the VNV is integrated throughout the development process. And we in MathWorks, like we've provided the framework to have a digital thread which ties in from all the way from your concept when you're building a medical device or a new algorithm. You tie in the requirements, and as you're building your firmware algorithm, you can kind of connect back your requirements to the algorithm. And once you automatically convert those MATLAB algorithms into the C code or C++ code, the same requirements are still linked and are traceable to the generated code. And then in parallel, you're also writing your test cases like unit tests, system tests, integration tests, and those test cases are also linked to the requirements. And those test cases can not only run on your MATLAB code, but also on the generated C, C++, or CUDA code, such that in the end, like when you're done with the whole process, you have all the reports you need, which becomes part of your 510K submissions down the road. So Holoscan, why Holoscan? And I won't spend too much time on this because like today is the day we are talking Holoscan a lot. But one of the benefits we get with Holoscan is, first of all, from a hardware perspective, it is directly integrated with all the sensor IOs. Which are needed in a typical medical device, be it ultrasound, be it surgical robotics. But then also the infrastructure, the architecture which it has is quite scalable and reliable. So with the microservice architecture, we are able to build several operators for wide variety of tasks we want to uh, deploy on the medical device. And the scalability comes from the aspect like you can keep adding more and more operators. And as you add more complexity to your device down the road in the software development lifecycle phase, you don't have to re-certify or re-verify the entire device itself, but you can just add another new operator as a plugin and just make sure that you certify that operator without worrying about recertification of the entire device. So as the device also evolves with time, as your algorithms evolve with time and the complexity increases, I think this Holoscan is a perfect platform to be able to enable that integration and incremental upgrades which you would provide to the device down the road. So what we will cover today. So MATLAB Holoscan device development is something I want to show you it in a little bit of details. And like I said before, the full workflow would be to link requirements, then you do the prototyping, and then we'll see in action how we can automatically generate CUDA code from MATLAB, integrate with Holoscan, do hardware in the loop and processor in the loop verification. And then once we are verified with our algorithm, that's when we wrap that MATLAB function into a Holoscan operator, and then we render it on the Holoscan and the GPU for a cinematic, like a live stream or a direct connect with a real-time sensor. But because it's a very comprehensive workflow, you can always reach out to me if you want more details. But today, I will show a part of it where we'll focus on the designing, code generation, and verification, and generating the Holoscan operator piece. So one of the examples I want to take here, actually, there are three examples I will cover in the next 30 minutes or so. Uh, the first one I want to talk about is updating an existing beamforming algorithm for ultrasound system. So this scenario is where we have already a ultrasound system, and going back to my ultrasound example, right? Let's say as a R&D of a ultrasound design company or a researcher, you want to try out a new beamforming algorithm and you want to deploy that in your existing system. So the way to do that is first we want to design and prototype algorithms with simulated data. So get some, virtual data, simulated data, and make sure that the algorithm is doing what it's supposed to do. In terms of when we talk beamforming, it is mostly signal processing. So we are verifying that the signal to noise ratio is coming out to be what was expected. The image is getting focused and so on and so forth. Then the next step is to, once we verify that algorithm, you take the GPU coder tool, and that is what will convert your MATLAB algorithm directly to the CUDA code. And as you translate into the CUDA code, there are some optimizations which we will discuss, but then you can also do the hardware in the loop verification on a Clara IGX hardware to make sure that the code is running against the actual GPU, which becomes part of the medical device. And then finally, once you're satisfied, you can generate the MATLAB operator in the HoloHub, and that MATLAB operator can be connected to direct like a cinematic streaming ultrasound from the IO sensors directly on the Holoscan device. And then you can run this new beamforming algorithm and make sure you're getting the throughput and the fidelity or the performance you were looking for. So let's look at these steps a little bit more in detail. So in terms of like prototyping with MATLAB, so to be able to generate even simulated data or synthetic data, first you need to characterize the ultrasound system. And we do have inbuilt capabilities from workflows from like phased array toolbox, where you can generate those various waveforms, the sound waves, generate a synthetic scene. You can model your antennas, you can model your sensors, and then we already have inbuilt algorithms for several like match filtering, image formation, beamforming, etc., which becomes part of that device. So once you prototype or characterize your device in a simulation environment, then you can generate a wide variety of scenarios. And in this case, like what we have generated is uh, one such scenario where we're doing a linear scan with 10 pin targets, and we'll try to test out our new beamforming algorithm on this pin targets if it focuses or not. And something to keep in mind here is just because we're doing linear scan, that's why we see these parabolas. And if the beamforming algorithm is correct, what we will see is these parabolas get focused into pin targets in the end. So now that we have generated synthetic data, we build quick algorithms in MATLAB. And this is like one such beamforming algorithm on my right side, which we have put together. But one of the things about the caveats to this beamforming algorithm is this is a not a frequency domain method, it is a time domain method. And in a time domain method, let me actually go back here. What I'm going to do is I'm going to iterate through every pixel in this image. And at every pixel, I will be calculating uh, uh, I would be calculating the throughout my sensors, like the whatever the number of sensors my ultrasound probe has, what is my phase correction terms, and then I'm going to do a superimposition of the data points across all those sensors in phase to get the focused data set out. So again, not to get too much detail in what the algorithm is about, but the key here is these two for loops on the top, which is indicating that I'm iterating through my x-axis and y-axis throughout every pixel and doing all these computations below it. So because of this, the speed of such an algorithm is very slow. And in my case, like my data was, let's say, of size 10,000 by 20,000 pixel, which I simulated. And you can see that it's taking 1,355 seconds to actually return back my output. Now, from a R&D perspective, that's very slow, and you don't want to wait that long to get a result to realize that you've made a mistake and you need to make more changes, run it against the test data one more time, and then you kind of iterate through it, and it will take a lot of time if you start doing that. But this is where the power of the GPUs come in. So there are two ways to leverage GPUs within MATLAB. The first way, which I'll show you right now, is while you're inside that MATLAB, you can automatically convert this MATLAB script or whatever MATLAB script you have into the native CUDA code and then compile it back into MEX. And MEX is a short form for MATLAB executable. And once you compile it back into the MEX, you can run that same function inside MATLAB environment, but at an accelerated speed. So let's see one quick video. I'll Actually, I'll just slow this video a little bit down. So this is the GPU Coder app, which you can open in MATLAB, and it's like a graphical interface which allows you to walk through the steps as you want to translate whatever MATLAB function you have. In this case, I have this function, MATLAB beamform TDBP cur, uh, into the native CUDA code. So when you hit next, because CUDA C, C++ is all, the types do matter. And that's what the second step is. You just have to specify your input function arguments, like what are the types. And in this case, that my raw data is actually a uh, complex data matrix of this size. And then my processing parameters is a structure which has all these different double data types and so on and so forth. And there are other parameters too, like my x-axis for calculations of some of the phase compensation terms, y-axis is my two-way propagation time. And then as I go through this app, it will ask me to check for runtime issues, but you know, it is a good practice to do that. Just because let's say if inside a MATLAB function, you are using some code which is not supported for code gen. As an example, if you're doing some visualization inside that function, like a plot function, So you don't want to generate the CUDA code for plot function. It's like it does not make sense. You want to keep it outside. So this is what this runtime issue is. Line by line, it will parse through your code and give you recommendations if certain function needs to be changed or any of the part of the code needs to be restructured for better performance. So once you get through that, in the generate tab, what you can do is you can specify your intent over here. And as you can see, there are several drop-down options. You can generate MEX is what I'm going to do, where you generate CUDA code and compile it to be able to run inside MATLAB. Or you can also generate the native source code, which is a CUDA code, to integrate it with external application. Or you can also generate these static and dynamic libraries or standalone executables directly from MATLAB as well. So as I generate the MEX and I hit generate, what MATLAB does is it parses this MATLAB code every line by line, and it will try to create a kernel for everything it possibly can without breaking the code. And as it goes through line by line, the first thing which it starts to parallelize, it will create a kernel, and then it will try to see if other optimizations are possible by default or not, but it is very automatic at this stage. So as an end user or a developer, I don't have to worry of anything at all at this stage, but I can let just MATLAB do the optimization. And now you can see this code has been generated over here. And this is like the native CUDA code. And you can kind of scroll through the code and you would see that it created like several kernels. These all static global are all my CUDA kernels which have been created. And one main kernel I do want to talk about here is uh, this outer kernel, which is parallelizing the two for loops. So if you notice over here, this if statement for this x-axis and y-axis, which indicates that my outer for loops are both parallelized. So in a way, what I did is I massively converted that serial code in MATLAB to be able to launch 10,000 times 6494 threads at the same time, leveraging the power of the GPU and run it in parallel. And because of that, if you see over here at the bottom, from the CPU time, which was 1,300 something seconds, out of the box, my runtime went down to 0.57 seconds, which is massive. And by the way, this is not using IGX at this stage. I forgot to mention, I'm still using an x86 GPU, which is an NVIDIA GPU, a GeForce or one of those. And more the number of the powerful GPU you have, the better performance you will get out of the box. Awesome. So the GPU code conversion is done and it is compiled into a MEX, which is still running inside MATLAB. And that's why I can just call this function inside MATLAB and I get this 200, 400, 2400 times speed up out of the box. But we don't stop here. There's another tool, the performance analysis tool. And what this does is you can run this performance analysis. It's like a profiler tool, and it will tell you any insights of if there is any more avenues of speed up. So like in this case, there was one kernel which was getting called multiple times. And when it's getting called multiple times, the CPU is still sitting idle and waiting. So this app or the performance analysis app would give you these insights, the performance timings, and then it will also give you prompt on what you can potentially change in your code to speed up the code a little bit more. So these insights are always helpful, and you can kind of always look back into it depending upon the application. Sometimes in this case, the two for loops were still straightforward for me to parallelize or the GPU coder to parallelize. But in other case, if you have like bunch of FFTs, image processing functions, you have more complex computations going on, then these tools become quite handy to figure out like, okay, how is the kernel creation going? What are the things you can potentially change in your code to get a better performance? So anyways, in this case, there was this multiple kernels being called, and we were able to change the source code so that the GPU coder can invoke a one kernel call rather than having CPU wait certain times. And I'm not getting into too much details, but it's just like we have certain pragmas in GPU coder where you can force the GPU coder to create a kernel of for one function before it creates for the other function. You can kind of determine some priority, and that way it was able to create one big kernel and it was not like jumping in between the CPU and GPU, and it saved time. So 0.57 seconds, we got down to 0.0255 seconds on a GeForce x86 GPU. All right, so that's where in MATLAB, basically you did your optimization. You are still in the research phase. You're making change to your MATLAB code, generate the mex, run it quickly, and understand if it's doing what it's supposed to do. If it's not doing, you change the code and you test and prototype either on synthetic data, or if you already have some saved data, you can run that as well. And the save data also, actually, I forgot to mention, but a lot of times there is a lot of clinical data which is available. And when we are prototyping new algorithms, we want to test it and verify against those clinical data. And with this GPU coder, you can also parallelize those 100,000 patients you will be running your algorithm against in parallel and get the maximum throughput. Awesome. So now that we are done with the CUDA code generation, the next step is to, because again, it's a medical device, we have to do more verification. Ideally, we would have linked it with requirements, but like I said before, I'm not going to show that today. But we will do the processor in loop verification on the IGX hardware. And the way to do that is this app itself, the GPU Coder app. It has this capability in the settings where you can specify, you can connect your IGX through the TCP IP, and you can specify your device address, and it would SSH into that device, whichever platform you're using. And because IGX also has an ARM CPU on it, so it will automatically generate the code with the C code for the CPU ARM part, and then the GPU code would still be the native CUDA code. So you make these changes in the settings, and rather than, remember, you can generate this uh, this a compiled code, which we call as PIL, or processor in the loop, and you're still running the algorithm from MATLAB, but now it's not running on your x86 anymore. It is feeding all your clinical data or test data to the actual IGX platform, and you're getting the results back, and you're comparing it with a certain baseline or certain performance, or what your objectives are with that code. So basically, at the hardware level, given the constraints of the data types, fixed point representations, and whatnot, you're getting the right performance, and you prove it out again and again. So once your algorithm is verified, now it comes to the last two steps, which is now you're taking the algorithm away from MATLAB and putting it in a deployed application. And then the step is still you stick with the GPU Coder app. You still define the data types the same way. But one of the differences here is now I won't generate the mex anymore. I would generate dynamic library or .so file for Linux. And what that does is it will, of course, it will compile the code. It will generate the DLL dynamic link library. And you can even note, like, one feature I did not mention earlier, but these code generation tools are also traceable. It is traceable with requirements, but then also every single line of CUDA code which gets generated, you can click on that CUDA code, and then you can map it out to which part of the MATLAB code was getting parallelized, or the CUDA code was getting generated. So this DLL is now standalone. The source code is standalone. It has no dependency of MATLAB at all. And this is where we can port it out, and actually GPU coder, because you're already connected to the IGX, it directly puts your compiled DLL and the code, the source code, like if you see over here, beamform.so file, in your Clara IGX target or the Holoscan target. And once you're in this Holoscan, uh, you can always kind of now move out of MATLAB, go in your Holoscan SDK folder, and the next step you would do is you would take this .so file or the compiled file and all the source code, and you can rebuild your beamforming application, which was running already on Holoscan. And so basically, you have this uh, Holoscan, the main file is already provided. You have this .so file, which is the source code, or which is running that beamforming application. And then you build it using your CMake file, and then the YAML files compiled together to connect that. The main thing what we're doing in Holoscan SDK is basically taking that wrapper application of .so file and connecting it with the streaming IO sensor data, which is coming from the Holoscan sensors directly. So that's what you can do. And in this case, there are two workflows which we have provided. One is we still use some simulated data first to make sure that the Holoscan application is running. And then once we are satisfied, we rebuilt it with the IO sensor data. And this IO sensor data in this case uh, is ultrasound image with some phantom pin targets. As you can see, these are the pin targets, and we're doing some contrast comparison as well with that beamforming. So the application is rebuilt on Holoscan, and now we are actually good to go. So in summary, what we saw right now for the first application, taking that raw MATLAB code, accelerating it on the GPU in x86 first to get to accelerate your prototyping and the research phase, automatically generating a dynamic link library with GPU coder, putting it on the Holoscan, and rebuilding the Holoscan application uh, 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 and connecting with the real, like the real sensor Holoscan IOs. That's how you can kind of quickly build, prototype, and deploy your any application. But one of the things I do want to emphasize again is, like this was a purely signal processing, image processing kind of example. But this workflow is very powerful in terms of it extends to a wide variety of different workflows. So we are not limited to signal processing, image processing. In this example, which I have over here, you can also build ultrasound segmentation algorithm using AI, and you can use AI to auto-generate the CUDA code as well and deploy it on a HoloHub to integrate with a like a cinematic ultrasound viewing. So let me show you like one of the capabilities in MATLAB. So this application, I won't go too much in detail, but we already have the framework inside MATLAB to be able to build deep learning models, machine learning models from scratch. We have tools to work with medical images, radiological images, endoscopic images directly out of the box, such as labeling, and some of that I will show later on. But once you do that, you can take your MATLAB algorithm with the deep learning algorithm, which is doing the classification or segmentation, and auto-generate it to the CUDA code. But one more powerful aspect about this workflow is you can also, if you do not want to build your algorithms from scratch from MATLAB, you can also bring in your models directly from PyTorch, TensorFlow, and ONNX format. And MATLAB GPU coder, which we just talked about, it would automatically convert any TensorFlow PyTorch models into the TensorRT or the CUDNN libraries for the native CUDA code and deployment on NVIDIA GPUs. So one of the workflows which is used extensively these days, and especially for deployment since the code is open. So from a regulatory standpoint, this deep learning code, which is open and readable line by line, is a high value for device manufacturers. So this is one of this case with there was an existing, again, an ultrasound system. It was not doing any AI, and a device manufacturer or researcher, you quickly used Holoscan and MATLAB together to build an AI segmentation, and you just upgraded your existing ultrasound device to include AI segmentation capability. Awesome. So one more last application I want to show you, and this is kind of, we start simple with signal processing, went to AI, but let's get more complicated, where the real value of this MATLAB and NVIDIA integration, like when it starts becoming, the ROI becomes a lot. So this application is this surgical robotic application with real-time sensor processing. And the main thing about this is there would be, let me just open this. There would be sensors involved, which are the perception sensors. It can be video sensors. It can be radiological medical imaging sensors. It can be also these IMU sensors in the surgical robotics. And then those sensors need to be integrated to build a closed loop surgical navigation, surgical controls algorithm. And as you build those in real time, you need to also deploy it on a platform such as a Holoscan, such that as the new data is coming in from those sensors, the controls algorithm are able to adapt in real time, and in real time we can perform the uh, uh, the surgical navigation or the surgical robotics workflow. So this is one of the examples on the right, and I will share the link of the paper from which it's coming from. But this is an actual Da Vinci robot put together by Intuitive's robot, like the main Da Vinci robot, and it integrates with endoscopy using MATLAB Simulink to build like the surgical navigation algorithms and collision avoidance algorithms, and in a closed loop manner. So to build this complex surgical navigation system, there are a bunch of workflows required, and I won't be able to cover all of them today, but I'll try to give an highlight of some of those workflows and how it's made easy with MATLAB and Holoscan when we work together to accomplish that. So on the left side, like building those AI, AI or computer vision algorithms from a direct video stream or a radiological imaging is, there are tools available in MATLAB out of the box, where you can automate some of those labeling or segmentation pieces, which is the first step. And especially when it comes to the surgical navigation, building an algorithm for surgical navigation. So you can use AI-based techniques or even the non-AI based techniques such as active contours and other traditional computer vision workflows, which are very powerful in doing this segmentation, and it can all be done through an app. But then also you can use Monai label to in this app to do more advanced labeling. So this video over here, what I've got is the Monai label is supported out of the box. You load in any of your radiological images. You define which tissues you want to segment out with the Monai capabilities, and it it does use a GPU at the back end. MATLAB directly supports that, and then once you figure out the tissues you want to segment, you just run that Monai network, and then you will get the appropriate segmentation on your CT or MRI images. So Monai label is also supported out of the box out of this to make the workflow easier. So segmentation is done, but beyond segmentation, a lot of times, especially when we're dealing with surgical navigation and planning and working with like pre-op, post-op, and inter-op uh, workflows to help the surgeons, we also encounter a lot of registration problems. And in MATLAB, we have given again apps and several methods of registrations to make this registration of CT, MRI, PET, X-ray, ultrasound, whatever radiological modality you're working in, a lot much easier. So as an example, in this app itself, you can have deformable registration algorithm. You can fine tune it, and you can kind of like the example on the left I have is um, doing the registration of the lungs while it's expanding and during the inhalation and exhalation. And it can be used for a wide variety of surgical navigation and planning workflows. As an example, one more example comes to my mind is recently we were working on a project where there was a CT scan of a brain with a tumor, and that CT scan, they had already labeled out the tumor and the surgical plan. But during the surgery, they were taking the ultrasound of the skull and the brain, and with that ultrasound, they were registering the CT scan segments of the tumor on top of the real-time ultrasound scan to be able to help surgeon navigate on how much resection of the tumor is left and what's the next course of action during the surgery. So that's quite phenomenal. But again, as you can imagine, a lot of surgical navigation workflows and then also real-time sensor processing becomes critical for these things, right? So registration is another key part of it. And then comes like, so we covered segmentation, we did registration, and now talking about controls, which is a whole beast in itself. So controls, what we covered so far right now was just this part, the perception piece. But now you get into this control algorithm where you have to do motion planning, such as path planning, trajectory planning. There are controls algorithms. There's usually the surgical robotics, even though if it's controlled by a surgeon, it's not fully automated, but there's a lot of precision controls going on behind the scenes. And it is any disturbance coming from the surgeon input, these control algorithms try to mitigate it. So as an example, if the surgery, the in the surgical field of view and the plan, the surgeon accidentally moves the robot a little bit out of the field, the robot will automatically correct for that variance, and it will keep the surgical like the equipment in the field. So any disturbance coming from the surgeon is also mitigated by the robot and makes it very, very precise. Then there's collision checking, like especially robots like Intuitive, where there are like more than one arms and multiple things happening. You want to automatically avoid collisions. And then all of this kind of feedbacks, it's a closed feedback loop, and it goes back to the, feeds into the trajectory planning, path planning, so on and so forth. So inside MATLAB, we do have this tool, Simulink, which allows you to build these complex controls algorithm in closed loop. There's this discrete logic, time logic, like state flow, which I have on the screen. Uh, and you can build those complex controllers. You can monitor on how these different states are transitioning for supervisory systems, for safety systems, for collision detection systems, and so on and so forth. But then also you can do the fine tune of the controllers with automatic tuning of, simple controllers like PID, but other more complex controller like even MPCs and stuff, and all working together. You can leverage the capabilities for doing inverse kinematic simulations as well, inverse kinematics and dynamics simulations with that multi-body models of your robots all combined together. So the actuators, the joints, the forces, the pressure, um, everything which goes in the behind the scene in controls, all while integrating with whatever perception we're getting from the AI and computer vision algorithms with that registration or segmentation, which I had talked about. So that's all of it combined together is what this Da Vinci systems becomes. A system like Da Vinci becomes where you have multiple arms operating together, endoscopes, or sometimes even other radiological modalities guiding this surgical robots for doing some precision surgery applications. So all of this was done so far in MATLAB and Simulink, but going back to the Holoscan where it comes in, each and everything which I talked about, from registration algorithms, controls algorithms, segmentation algorithms, you can package it up as a MATLAB function, generate the GPU code or the CUDA code to put on Holoscan, the same way we did to generate the DLL. And the best part is even the Simulink model supports this code generation. So all the controls piece, which is might be living in Simulink, you can still generate that GPU coder DLL and deploy it on your real-time Holoscan hardware platform. And just as we did before, once the DLL is generated for surgical navigation, planning, registration, everything combined together, now you can go to your Holoscan SDK folder and rebuild that application and have a real-time sensor streaming data integrated with a very complex surgical navigation or a surgical robotic application. And keep in mind, because MathWorks like MATLAB is connected to Holoscan directly, so even doing like fine tuning of your control systems with hardware in the loop workflows is totally possible. And you can run your actual hardware in real time, tune the parameters of the controller in real time, and get that precision controls and the precise navigation algorithm which you were looking for directly out of the box with MATLAB and Holoscan combined. So here's one such customer reference story, as we would call it, from Corindus, which is now which is now Siemens Healthineers. A disclaimer: at that time, they were not using Holoscan, but they were still doing the same workflow with MATLAB Simulink. And now with Holoscan being there, I think they can also leverage this Holoscan capability as a part of their device. So it is a tele-robotic surgical platform where the surgeon does not perform the coronary intervention surgery. And the problem which they were facing was surgeons have to wear a very heavy lead jacket to prevent all the radiation which comes from the CT machine, which is linked with this device for navigation. So now the surgeons can actually step out of the room and perform the surgery in a remote place, uh, and uh, and they built this surgical planning, motion, correction, and integration with the CT, with labeling and segmentation, all in MATLAB, and they deployed it on their custom hardware targets. And one of the things which hit the news was in India, this company Corindus, now Siemens Healthineers, performed a remote surgery with almost like the surgeon was 50 or 60 kilometers away from the patient, which was pretty cool. But all of this can be done quite easily and straightforward, and using MATLAB Simulink and Holoscan, and you connect with those I/O sensors and get the maximum throughput in a shortest amount of time. Awesome. So with that, I'll quickly wrap it up. So the key takeaways with these three applications I showed you is automatic conversion of MATLAB code to C, C++ CUDA is possible. That's the number one enabler. And then we have the capabilities to optimize the generated CUDA code for maximum speed up. So you don't have to worry even about if you are non-CUDA programmer, don't worry. The tools are there to help you get there. And then whatever application you're working on, surgical robotics, ultrasound, X-ray, MRI, these generated CUDA code can be wrapped into MATLAB Holoscan operators inside the Holoscan SDK platform. And then you can get this faster prototyping, validating, testing, deploying of these algorithms. And with the Holoscan directly becoming part of the medical device, you get the faster time to market of your medical applications. So that's all I had. For additional resources, I think the slides would be shared. I've got some examples linked here. We have good starting points for GPU coder examples for doing some optimization, or medical imaging examples for building those segmentation and registration algorithm. And then we also have a sample application on the HoloHub page. The link is provided here. And then we also have this SDK user guide to help you get started. And there are more tutorials on if you'd like to learn more on what is GPU Coder, how do you use it. We always can help you with it. So that's all I had. Here's our email. Myself and Mark, we've been involved in making this happen. So you can always reach out to us.